today will be pretty light-hearted. I mean, compared to what we have been seeing for the last few lectures. First of all, this is, although you see some GAN in the boldface and large fonts, this lecture is not about GAN. On Monday, you will learn the general theories and features of generative models from Ilham and Oishik in great detail. So this can serve as an appetizer, but nothing serious about generative model. So when I was thinking about what I should do on the last class, I thought we were all discussing about sets and graphs for all this time. The only thing probably, and whenever we were discussing, we were talking about jet classification, jet mass regression, etc., node classification. So those were all inference tasks on a set problem. Now, I wanted to show you an example that once you build a basic message passing layer, how do you use it in a real life problem? And then I picked up that why don't we talk about some generative model on set generation where we can show you how a message passing has been used, or what are the general rules to use a message passing layer in a full task, all this stuff. But then I realized that since you were not introduced to generative model, at least I'm sure some of you know it, but I expect some of you also don't know it. So I thought, why don't I set up a toy problem? Since the first lecture was about MNIST can be thought of as a point cloud in 2 dimension. So I have set up a toy problem where we will try to do some set generation where the elements of the set will live in a 2D feature space. So this is, you remember that the MNIST was a point cloud which was living in the 2D feature space. So similar, but I could have generated it for MNIST as well. But I thought, let's have some fun. Let's make some synthetic data. And this is an example which we used 4 years back at Weizmann. So I just wanted to repeat that. Okay. So in general, when you take a data sample, the whole point is that probably, I mean, in all reality, that data sample is a finite sampling following some probability distribution. Now, our task is to generate synthetic data which we haven't, which doesn't exist. We will generate some artificial data, but which should follow some probability distribution. The difficulty of this problem that we don't know this probability distribution a priori. However, we will let our neural network see some data samples, ask us to learn what can be the probability distribution is following, and then generate few instances of data, new data, which will follow that unknown probability distribution. This is the core broad problem of generative model. Okay, so let's say we generate some points, and we are not downloading any data, but you can play with yourself. So without showing the data, look, we are generating like 700 points, and we are making 2D point like coordinates, and just let's see what we have generated. This is a game with NumPy, nothing else. So if you scatter it, you will see this plot. If you now, what does it remind you? Probably a smiling face or something. Now, I don't know, this is smiling face of what? Because this can be a smiling face of a human cartoon. This can be smiling face of a cat. I mean, you can impose this structure on a human face. You can impose this structure on a cat face. Doesn't matter. What does matter is that we don't know this information a priori. And we want to know, if we are shown such a data sample, from which probability distribution these data samples are drawn. Is it from human face, a cat face, a bat face? Who knows? But we want to train a neural network which will learn that there is a pattern in this distribution and eventually try to generate synthetic data which will look like this. Okay, so is the problem clear? You're shaking head this way, so I don't know whether it's yes or no. Okay, good. Is the statement of the problem clear? So we are trying to write a generative model for 2D point clouds, a set where we don't know from which probability distribution this instance of a set has been generated. Right? Good. So now think of the following image. If you download an image like this, plot it, it's an RGB image. So this has a shape of like 3 channels, 281 cross 300 pixel. But if we just take a random number and plot it of the same shape, this looks like some noise, random distribution. So in the spaces of distribution of all 3 cross 281 cross 300 numbers, some of them have human interpretable meaning, some of them are complete noise. So we don't know how to teach a neural network. So right now, we don't know what probability distribution constraint to impose on this noise to generate a meaningful distribution of the point cloud you have just seen, right? So for that, we write down a model, a neural network, which will replicate the unknown probability distribution which we are searching for. Okay, and that's what we will call a generator. So remember what the generator is. It takes into some arbitrary distribution, let's say 2D, and it will try to put out a meaningful distribution in the 2D, which we are looking for. So this function, the neural network which we will write, that will replicate the PX, universal approximator of PX. And that's what we are calling as generator. And by now you know that multi-layered perceptrons are pretty good ones. So we have stacked up few linear layer and pass it through some activation, which is ReLU. So again, we try to model the universal approximator on this 2D sets as stacks of linears and ReLUs and try to see what comes up. So you see that once we put it, something like this comes. Now let's see, this first of all doesn't make any sense. What did we do? We made a function fx, which is a mapping from R2 to R2, right? It takes in a 2D noise distribution, it gives output some 2D distribution. There is no constraint on range, etc. So what? Yeah, sorry. Sorry. It's a one-to-one mapping. The number of points appearing here, same are appearing here. But since we just wrote a function where we didn't know what the weights are randomly distributed. So for an MLP, you pass some two-dimensional distribution, you get some two-dimensional distribution. Okay, so this is nothing but just we have written a function and where we are visually demonstrating that it's an R2 to R2 mapping. Now, we need to train this, we want to train this using an adversarial training. What does adversarial training means? We will simultaneously try to show the network some of the R2 pieces, like elements of this R2, which follow the kind of image which we really want the neural network to learn, the point clouds. And also on top of that, we need to teach the neural network some points which doesn't follow the pattern which we are seeking for, so that the neural network knows these are the categories which we should generate, and these are the categories which we should not generate. Okay, so and there will be a contribution from both these two pieces of information in the training program. So it's important to follow this part. So where did the chalk? So there will be a function g which will take those random data points as input, which right now we call z. Often in the context of adversarial network called noise. You will learn all these things on Monday in details, but I'm just giving you what g of z will do. It will give output some data x which has a human interpretable meaning. Okay, so this g needs to know which set of x are okay and which set of x bars are not okay. This is the information which we need to teach the network. Okay, so since we are playing with a toy data just completely for fun, so we also need to generate some x bars which should play the role of not the correct data. Okay, so earlier I showed you a smiley face randomly generated, that was the correct data. And now you see, if you go through the points, we generated some background points which were random noises within the range -1 and +1. So all those red dots you see in the image, those are also 2D point clouds, but those are randomly generated, not following the functions which we want to learn. It's uniformly noise scattered over, denoted by orange. And those ones we will label as like not the ones which I want the neural network to generate. So finally, I'm again repeating the statement of the problem. I want to write down an universal approximator f where it will generate some output, which are the blue dots. But to know the pattern of the blue dots, I really need to teach the neural network some alternative samples which it should not generate. Otherwise, it will be hard for it to generate these random points, because the whole point is that when the network will generate few points, it won't know where to generate, because all of these points in the point cloud has the location features. So it can't throw it some randomly, just like the orange points over the whole region, right? Yeah. Yeah, so you will when you will train the generator, you will show this is correct, and then we will see there will be a classifier which will distinguish this is correct, this is not. Because since this is a finite sample from an unknown probability distribution, the blue dots, we need to teach that, let's say, kind of analogous to the eye of the problem, can't be at the left bottom corner. So when we created this, we will use this for the training. We will label the blue dots as the correct ones, and we will label the orange ones as the incorrect ones. So this is a labeled data which will be used for a supervised learning problem. Yeah, sure. I mean, this is a 2D place. It's scattered all over. And each point, be it orange or blue, has a coordinate, but each point comes with a label. This one is it's like the correct one and incorrect one. So, yes. So, right, so when each point is a data point, and when we will later ask the neural network that generate 500 points, it has to learn that those 500 points preferably exist in this band, either in this band or on these blobs. It should not generate those 500 points. Let's say it can't generate 50 of them in this corner of the diagram. So see, the pattern itself is a function of the, what do you mean by the pattern? It's some contour, okay? And the contour is already defined by the positions itself. So it's indirectly learning that. Oh, then it's a much more complicated probability distribution from which those are sampled, and it will be harder for a neural network to learn such thing. Yeah, so we are setting up a toy problem where we have this kind of pattern. Let's say this is one instance. Now it can be that another sample has, like, the eye can be a little shifted here and there, and the density of points in one eye is a little bit less, etc. But it's equivalent to like sampling from a smooth distribution, right? But as you see, the problem is here, it's what is that smooth distribution, we don't know. It's not like you're doing a sampling from a Gaussian function where you know the function. Here we don't know the function, and we want to learn that function, right? So that's the thing we try to do. Because unless you teach the network what not to generate, it will end up generating some part of that as well. So we have a function f, right? Now you need to, it will give output something at the end, some points. But you also need to tell the map, you are not supposed to give me output in certain regions using certain patterns. Okay, so that's what we need to teach the network, right? However, when we train it, now that we have built a synthetic data where some of the points are labeled as correct points, some of the points are labeled as bad points, the one network should be able to distinguish that these are the correct points and these are the bad points. And in an adversarial network, that's why you have a second piece of neural network, which is called discriminator. Okay. So the discriminator function can distinguish between a true data and like a false data. So if you show a data, it will give you a classification score, whether this is a true data or whether this is a false data. Okay. So now the whole point is that if I know that I have a trained, now think of the problem of such that you have a network D where you feed this data and you tell it blue data is the right point, orange data is the wrong point. So it will be a supervised classification problem. And if you train the discriminator with this labeled data, ultimately it will be well trained, and on a general test data, it should be able to tell, given a data as input, whether it's a true data following the blue pattern or whether it's the orange data following the incorrect pattern, right? So we will have another piece of neural network in the problem. So this is called discriminator. And this will be called generator. Okay? Could I explain you what will be the role played by two pieces of neural network when we are trying to generate a 2D point cloud? This is all, we are not doing any serious stuff. These are all like toy data. But I want to prove, I want to give you an essence of a proof of principle, what's going in the conceptual level. Okay. Now, the classifier network, it's again some sort of multi-layer perceptron. You can see stack of linears and ReLUs, the activation, and the first dimension is dimension 2 because we are working on a 2D point cloud, nothing. That's why it's 2. If the feature space was something else, you should have done that. Now, first what we do, we need to first train a classifier, and we gave enough number of data points, what we generated, so that we teach the classifiers a priori, without touching the generative part, that which one is the right data and which one is the wrong data. So that, yeah, anyone question? So the discriminator has been trained independently first, so that later it can be used for the purpose of distinguishing which is the right and which is the wrong. So once you do that, and then you test whether it has been classified properly or not, you can read this snippet of code. Okay, what we have tried to do is that once a classifier has been trained, and since this is a very crude, rough level of problem, when we trained the classifier, we didn't had a validation loss or something. We just trained the classifier for few epochs and stored the state of the discriminator network. We didn't check whether it has been overtrained or not, because this is a toy problem. I don't want to get like, oh, I need to have 1% precision, nothing. This is just a toy proof of concept. So we just trained the classifier and the classifier in some trained state. However, I want you to look into one thing. When the classifier was trained, the data I want, I want to show you one point, output versus y, and just give me one moment. I wanted to make a point. So here you see how we created the labels. That was important. That when we had all these points, the signal points were labeled 1, the background points were labeled 0. And so the discriminator was trained with the right truth labeling so that it knows which one is correct. Okay. And then what happens? We again make some test data, ask the classifier to show that when the data points are in this region, whether it can identify what's the score it's predicting. So if the data points are lying in this region where our probability distributions are, we wanted to make it a color plot where the score is greater than 0.5. So this plot tells you that the classifier is now kind of trained that if the data points are lying in a region where I want my data points to be, it will identify it with a probability of greater than 0.5. So now the classifier is trained it can really classify which are the data points lying in the region where it should be versus which are the data point where it shouldn't be. Okay, so if the data points are in this region, the classifier paints it with yellow, and yellow is a color code here where the output scores are greater than 0.5. So the classifier now, after a short training, sort of knows that when the data points are lying in this region, I have to label them as true. No. I didn't still go there. The input of the generator will be latent space. We will come there. When I say GZ, okay. And here latent space is not a learned latent space. Z is just a pure noise. But we will come to that discussion. Right now, we are just at the discriminator level where it is trained with these are the right points, these are the wrong points. Please learn it. Later, we will ask you to classify which one is the right point and which one is not. Right, here we were. Now, what's the proof of concept? We have to train our generator so that it can produce some of the realistic outputs. Oh, sorry, I put that image short, but never mind. Let's look at the principle, so that I can give you before. It's important to have this picture in mind, what we are trying. We have a function dx now, well trained, which can classify which are the right points and which are the wrong points. Now, the whole issue here is we will have some g of z, which will take input some z, which is a random noise. It will give output some synthetic data, artificial data, which we are just generating. Let's call that x fake. And then in our real world life, we have real data which is following the distribution, which we know. So there will be a function d which will take into account x real and the generated one, x fake. Okay. And it will give you some output. And the whole part is that the generator will keep trying to output xf in such a way so that even a well-trained discriminator cannot distinguish between x real and x fake. Is this statement clear? What's the role simultaneously tug of war going? Yeah, so right now we have initially, the way I'm setting up the problem, that first we have a pre-trained classifier which already knows how to distinguish between a real data and fake data. Yeah. Yeah, so now I'm just talking about training the generative part, that how do we ensure the generator produces realistic data? In general, we saw a R2 to R2 mapping where it was producing nonsense data. Now the whole tug of war will go on that a well-trained discriminator should always be able to take, oh, generator, you gave me a fake data. I have real pieces. And the generator will try to improve itself more and more via this adversarial training where you get the feedback so that it will try to beat the discriminator, that at some point the discriminator will fail to tell which one was the real data and which one was the synthetic data, which it got from the output of the generator part. Is the concept clear? What we are trying to do? Okay. So you will learn these concepts from Elam and Oishik much more. Like I'm just giving you like a very high level overview of what's going on under the hood. But this is the concept going on. Now you can see we made some training of the part where we have trained. I mean, since this is a toy data, it was pretty fast to train on the computer. I got up to 2000 epochs, etc. But here you see we have a loss function where we are trying to train the classifier. Like the loss is computed from the output of the classifier, and we trained it. Okay. So now when we just give some random noise, it starts following the pattern where things should lie probably. And we will see this in more details. Like now with some short training, it was a 2D noise to 2D output set. The YOLO regions are ones where the classifier classifies them as true ones, and the output points are starting close by here. Okay. And now so this will be done in great details on Monday, but the final adversarial network training happens in the following way. So there is the classical, I think 2014 paper by Ian Goodfellow, which introduced this min-max loss. There is a simultaneous, so until now what we were doing, we pre-trained the discriminator, the question you were asking, and then tried to train the generator itself. But now if we give a simultaneous training where we have a loss function from both the discriminator and the generator, so there is a tug of war happening between these two. And this is the kind of canonical loss function, a min-max loss function we want to optimize for. And here, I'm just talking in context of some 2D point sets, toy data, and this X can be anything. It can be an image data, it can be some graph data, anything. So here I want to make a point that when we talk about general machine learning principles, like different methods like VAE versus generative model classifier, these are machine learning methods which are universal with respect to the input data. And in what sense they're universal? If your input data is an image, then you will build the block of these neural networks using 2D convolutional layers. If your input is like a set, probably it's better to build the neural network using deep set layers. If you know that your input data structure is a graph, then you build the whole network using message passing neural network layers. So there is nothing great about all these CNNs, GNNs, deep set methods. If you know a priori that your input data structure is a grid or a graph or some point sets, you will choose the individual layer accordingly so that it can efficiently process your input data. Okay, so whether you're using a adversarial training versus some deterministic task, it's independent of the object structure which we are using. So you should keep this like 2D thing in mind. Like you have grid, graph, and other set and other data structures. And on other case, you have the like VAE methods, then GAN methods, and whatever machine learning you want to do. So you can just do a nest of every data structure, you can write anything. And whenever you pick up, say, you want to do a GAN with a graph, the individual layers you will use to build the whole neural network should be message passing layers. Okay, so keep this picture in here. No, when we will do this training, simultaneously training, there will be backpropagation in the discriminator as well. No, you already started with a pre-trained state, right? Yeah. No, but that training may not be a full training because you don't have the data set, right? You just did a initial preliminary training to just set the state of the discriminator, and then you want to improve on top of that. And in this training, you will show it more and more real data, and the generator will produce more and more fake data. And finally, this loss, adversarial, say, feed for, like, forward, not feed forward, so the information from the output to the input, okay, feedback will ensure that the generator is also pushed in a state where it will start producing fake images which looks like real images, so that the discriminator can't anymore distinguish between the real and fake images. Okay. Yes. Oh, just to this is like making the training more efficient. If it's completely random or discriminator, then it may be that the training is in like a state where it just doesn't converge. So it's a good practice to train the discriminator a little bit a priori, so that when you will make the simultaneous training, it will the convergence of the training will happen smoother. That's the like practical point of view. So when here the second step of training will go on, you will have backpropagation both on the discriminator network and the generator network. So there are weight parameters sitting on both the networks, and the weights will be updated in both of the networks. The classifier input is, again, you have real images and the images coming from the generative model output. Then it doesn't know at all which one to tell, which one to label as real data, fake data at all. And there's a fancy name here called Nash equilibrium and stuff like that, which I don't understand, but which essentially means the whole training can drive the generator and the discriminator simultaneously, where the generator is producing completely nonsense, and discriminator will start learning that output to be the true ones. The whole training can be pushed in that direction. You don't want that. So you first update the state of the discriminator in such a way that already it knows a little bit how the real ones look like versus how the complete nonsense ones look like. And then on top of that, so at the initial part of this simultaneous training, the discriminator will always have a winner situation. It will always tell the generator, no, no, you are doing wrong things. I have seen good real things before. And once it passes this information to generator, the generator starts updating itself, and eventually it will start producing outputs where the discriminator can't distinguish anymore which one was real data existing in nature versus which one the generator has just produced. Okay, so this is the principle. Oh, it's the loss. I forgot to put an equality sign, sorry, in the formula. So, so, so it's just, there are two parts in the loss. One is the expectation value on the log of dx. This is the discriminator part of the loss, where the x is from real data sample when x follows p of data x. And then there is a generative loss where you have samples from the noise, so that when you draw that, you pass it to the generator G. It produces some fake data, and the discriminator will try to say, oh, I generated a fake data. Okay, so that's why that term comes with a 1 minus thing, because it has to be the scores from the fake data. Yeah, so that's sorry. No, then you have to keep the 1 minus in the other definition, because the discriminator is supposed to tell you whether it's a real versus fake. Okay, and the more and more fake data you generate, so that should maximize the loss. Like, you want your loss to be minimum, but if the generator keeps producing more and more fake data, that part should push towards higher losses. And so that simultaneously one part will try to win over the other part. Okay. Now, so you can see that there is a classifier loss and a generative loss, which are these two parts. I won't go into detail, but once you do the enough training, you will see that you start producing the results. So I had, let me see. Okay, yeah, this works. So I want to show you the following, that after all this training is done, when at epoch 0, when my training was not started, the output in this diagram will be just one of those images coming out of GZ. Okay, so I give input some noise and try to see what is the output of GZ happening. So if the training goes on and it reaches to some equilibrium value where it can then output meaningful images, right? Are you with me or not? So the whole part of training, the generative part, that I will give input some fake noise and it should produce realistic point cloud distribution. So at epoch 0, it was giving output some nonsense. And we will try to see at once the training goes on, how the state of the generator evolves so that it starts producing realistic part. So let's go to a training state of 60. Now the output distribution looks like this. Still nothing meaningful, but instead of a complete random noisy distribution in one side, it has some pattern. It started following a ring. Okay. And when we go, because we never constrained it to predict coordinates between 0, 1, 0, 1 in this direction. Since the state of the network is not still very well, it's producing point out of the region of interest. Okay, so, sorry? It can. I mean, just we gave some, I don't know, 600, 700 points, and this is already after 60 epochs, you see, training. And let's see how the training evolved. So I like this example because it's small to do, and let's go it to 170 epochs. Already it started producing something in the region, and each of these images are drawn from, I again start with some random noise, feed the generator when the generator state was at 170th epoch of the training. And starting when in 0 it was complete noise, it started producing something meaningful. So this also visually shows you how the state of the, you always see the loss function is decreasing, but it's interesting to see at each iteration of the training how the output is evolving. That's fun to see. And since this is a small network, it was good to do on my computer itself. And finally, you see it's converging more and more. And finally, like, so there is not much change between the 500th epoch versus this large number of epochs. But the whole point is that once we train the generative model on each instance, once it's reached the equilibrium, it's producing synthetic distributions, which looks like my original distribution. And if your original distribution required much computational intensive process, CPU hours, to produce that data set, producing these data sets are a matter of much lesser time. And we will see that comparison in realistic time. And our community, particle physics community, cosmology community, are gaining a lot from this kind of methods. To be concrete, which we will show, like our Gian simulation takes huge amount of CPU hours to process one event in CMS and Atlas. And we will show an example which was done in real life to just generate data sets which are much faster. So the Gian simulation, the output of the Gian simulation, you put truth particles through the detector simulation, and outputs are the calorimeter hits. Okay, so now you want to produce the distribution of those calorimeter hits, but you want to bypass the step of Gian simulation, which is computationally extremely expensive. You need hours to do that for each event, and then you think how many Monte Carlo events we need? Millions. When producing those synthetic data, no, not at all. So the whole point is that your generative model will produce distributions which are at par with Giant distribution, but you're not using Giant at all. But before going that example, this is a proof of concept which I wanted to establish to you, that if we define some distribution whose exact analytic form we don't know, the generative trainings are able to produce samples out of those distributions which it tries to learn. No, so in general, it's hard to overtrain this GANs kind of thing in real data, because anyway, to reach a good training and get a GAN, I think Oishik is a super expert. He's not here. Okay, of this kind of things, he will tell you that what are the complexities of training a generative model in general. But of course, if you plot the overall training, you will see at some point, I don't know, if you're lucky, you will see the loss is increasing where you know there is some overtraining. But in general, say for realistic parts, I haven't seen someone successfully overtraining a GAN for realistic data. Sorry? In the min max. Yeah. Right. Yeah. No, each epoch will have a backpropagation on the generator and discriminator. Some no initial weights. Weight in of initially training the discriminator a bit. Yeah. Otherwise, it will be impossible for you to get something realistic. Okay, but for a toy data I showed you, once you do that little part, then, and this, through this matplotlib widgets, we could show you that how the outputs are getting better and better once you go for higher training states. Sorry? Oh, then you will draw random number from that px. And why will you do all this? The whole point is that you don't know the px. You have a data, finite data in real life, which is following some very complex higher order probability distribution functions. I mean, solving P, if you know px, then you have solved nature. Essentially, you know exactly how nature behaves. The point is that we are collecting data and doing our experiments to know what that great grand px which universe follows, which we don't know. And that's why we are doing all this fuss. Right? So I just gave you a glimpse, an overview of through the problem of set generation, that how in general a generative model works. The same underlying principles can be used to generate, like say, detector calorimeter heads, and you can generate jets, the particles inside a jet. So you can try to bypass something like mad graph and generate matrix elements out of this, all sorts of things. People are trying all sorts of these things. So so now I will just try to show you some examples in this direction which have been tried in our community. Why can't I escape this? So let's, and I will show you some of the recent attempts in this direction. But this said, the examples which I'm going to show you, of course, are not the full example. So this is something my random pickup, okay? And you are welcome to go through the internet and figure out your own. One of the recent ones, which I liked a lot, is something called point cloud generation. They called it EPIC. You can look into the code if you want. I didn't want to show you more codes today. Enough of that. But someone just looking at this, if this is the whole network where you have P1, P2 up to Pn be the momentum of a set, and P1 prime up to Pn prime be the output momentum of the set, can anyone tell me whether this set to set mapping is invariant under permutation or equivariant under permutation, just by looking at this picture? Sorry, loud? Equivariant, right? So it was just like the Deepsets, the way we constructed, but the inputs are concatenated to a 5G network, which again is receiving some global attributes G. So the output of 5G is invariant under the permutation of the input sets, and that output has been again stacked to the P1 itself. So whatever 5Ps are getting, they are by definition permutation equivariant, and hence P1 prime up to Pn prime, the output set is permutation equivariant. So now that you have seen this kind of codes a little bit, you can try, without looking into the GitHub implementation, you can try writing a code of your own. It will have just two pieces of MLP, one 5P and one 5G, and that's it. So you can try to code up your own, that how to write it. It's a very simple there. It takes a set, gives output a set, and set plus an updated global feature. And you have been told multiple times during this set of lectures how to code this up. So are you confident now that some of you, that given a diagram like this, you should be able to code it up? Like the constructor of an NN dot module should have one MLP replicating 5G, another MLP replicating 5P. And the whole point was of this set of lectures come tutorials, that now when you see a modern day recent times particle physics paper applying graphs and set space method, you should be able to reproduce those things. You should feel confident that I can write a similar code without taking help, which will do similar stuff. And then when you have your own plan, you can write your own codes. Right? Good. Now, they did a generative model. The whole game they played, same as the discriminator and generator, which we talk now. They had their own piece of discriminator, they had their own piece of generator. But the point is that this discriminator and generators are built out of this permutation equivariant layers. And now all of you are masters of permutation equivariance, right? So once you write a layer which is permutation equivariant, the way we showed, you can write down a discriminator and generator of these sorts and do your own favorite min-max training. However, you notice one point, I encourage you to read the paper, that they have engineered the loss function a little bit of their own. And that's where you input your physics knowledge to drive the state of the network in a direction where you want to. So when you talk about physics-inspired neural network training, at least in my experience, where you really feed your physics knowledge is that pre-processing the data, which is, I think, the most important part. Then you implement the symmetries which should be present in your data and use that symmetries to construct your layer. And finally, you design a loss function where the output of the network should be close to the target, and that target should have physics inbuilt. So that's where you bring your own domain expertise to design the whole neural network training, where you do a pre-processing, design of the network, and design the loss function. So keep these 3 points in mind. Okay. Right, and this is some performance they got. So you see that they have a JetNet distribution. JetNet 150 means it's a sample of jets, quark, gluon, top, W, Z. These particles are fragmenting to form jets, and each of the jets can have up to 150 particles. That's all the JetNet sample is, and if you do a Google, it will give you a custom data loader for PyTorch, how to read those data sets. Now you see at the truth level, what are the distributions of the particles inside the jet? These are coming out of MATGRAPH and Delphi simulations. Now the generative model also, the EP GAN produce distributions which looks identical to them. With the right normalization, you see the y-axis is not normalized. But still, you could bypass the whole MATGRAPH and Delphi's chain, but could write a generative model which will output a set of particles whose distributions are totally following the rules of quantum field theory. Up to, yeah, it's a per jet thing. It's up to 150 particles. It's a distribution. Although it's a relative particle PT, which means it's the particle PT normalized by the jet PT, and that's why it's up to 1. Yes. Yeah, so the jet lies in a region of PT. Yeah, it's over a phase space. Of course, I mean, there is always some fluctuation, but when you look into the gray distribution, which is coming from the MATGRAPH plus Pythia kind of, they have their own fluctuations there. Do you trust the tails of a Monte Carlo generator blindly? No. The whole point of this distribution is that in the bulk region where you know, you trust the generators, you trust your Monte Carlos, there the generative model has also produced similar distributions. And that was the whole point. G of Z will give output which are almost identical to the real world. So here the real world distributions, probability distributions, are encoded in JetNet 150, where you have modeled your fixed order QFT calculations. And your generative model has learned to sample from that probability distribution. And nowhere there you have encoded any formulas from Peskin-Schroeder. Right? Sorry? What do you mean by fat jet PT bin? Yeah. For a particular jet, yeah. Right. Yes, there is a PT. So these jets are lying themselves in a region of phase space, in a PT region. And you're taking jet by jet, collecting individual particles in the jet, and plotting what is the particle PT over jet PT. First of all, there is no information here to tell you a fat jet. I never told you what is the R of the jet. Okay. I mean, the principle goes for any radius jets. And I don't remember top of my head what was the PT region where they produce their samples on, but it's over a wide range. It's not that they are sampling only at a fixed PT and looking into it. Okay. Sorry? So when you have reconstructed jet, there the IRC has been taken care of. So your target distributions are IRC safe by definition. The jet algorithm has taken care of it, right? Yeah. So I don't think they haven't at least talked in their paper how this model scales. So what they did, they built each instance of the training data is an individual jet, and it doesn't carry the information from what kind of physics collision process those jets are originated. They took single patterns, they shot, and they made jet out of it, and that's how they build their training data. The whole selling point is irrespective of which pattern it's originated from. They build a jet and they could smoothly extrapolate their methods along jets originating from different pattern species. Whether it's a top initiated jet versus a light quark initiated jet, gluon jet, W jet, if you take single jets, make generative models out of them, you can reproduce the kinematics of the particles faithfully. So the training samples, it's a mixture of all flavors. So otherwise it will be a biased. Sorry? I don't remember. I hope they make it like equal mixtures of different species. So, I mean, read the paper to know these details of the training. But I found their network to be simple enough so that I could demonstrate that to the broader audience here and could show that this is doable in real life. Different? Yeah, there is, of course, there is a correlation between if you plot like kinematic variables like 2D scatter plots, you will see correlations. Yeah. I mean, that correlations come from the mod m square of the QCD itself, right? So the whole purpose is that without explicitly writing down the formula, we want a neural network to learn that probability distribution following mod m square. So it will learn the probability distribution in that phase space only, where you have generated your. So a neural network can't learn an information which it has not been trained upon. Okay, so if you produce your training sample in a finite phase space region, then it will only learn the probability distribution, whatever is lying in that phase space region. I think so. It's not very easy to smoothly scale in the region where it has not been trained on. It will start producing nonsense in reality. Consuming. So you really want to bypass the CPU hours of a Monte Carlo simulation, but produce realistic distribution in much shorter time. Yeah. So let's say to be very specific. Huh? You might need large data set, but that's it. Let's say you want to produce 100 million events in some cases. Now, let's say with 10 million events for few days or a week, you run your MATGraph simulation, produce 10 million events. Now you train a network, say another week. But now once it's trained, the rest 90 million of events, you can produce much faster. You don't need to run the MATGraph simulation anymore. Right? We will see that. Also, also I think W jets they have. Maybe. Higgs. Yeah, but when I saw their samples, like they have their samples. No, no, no. Modeling heavy flavor is a bit. They will do it. Okay, so right. Now there is another paper which I find pretty interesting. Did I show? Wait. Yeah. Okay. I will come. Another interesting. So the previous one was a deep set kind of thing, and then another part trying to do exactly similar kind of task, but instead of a epic layer, they formed a message passing layer, and they made it. They called it message passing GAN. But same concepts. The individual layers are instead of a deep set layer versus a message passing layer. You have a generator, you have a discriminator producing jets. Okay. And this is the, sorry, I forgot to put the archive number. I will put the slide. Yes. So now you can see, at least I don't have the one-to-one kinematic distribution plots, but here you can see what's the gain in timing. So this is the point I wanted to point you out. Look at the time taken by Pythia in units of microsecond, and compared to that, to generate the particles, what is the time taken by MP GAN versus EP GAN? Do you see the scale of the problem on the y-axis? And that's the time taken difference. The right-hand side is a realistic example in our Atlas Fast 3 simulation, where we try to simulate what will be the calorimeter distributions of the energies. The vertical line, the top line, the black one, is the time taken by Giant4 as a function of energy. So when you throw more and more pions to Giant, there are much more shower spreads. And that's why it scales up. Look at the time taken by generative models. I'm not going into the complexity of what is the detailed architecture of Atlas Fast simulation, but see the realistic examples and see the CPU time. This is order of 60 milliseconds versus more than 10,000 milliseconds. You see again, what's the point of writing such networks? And this has been done without losing the reliability of the distributions. So when you are at something like 200 GeV, you are getting distributions of jet single particle responses, which will be equivalent to Giant distributions. But this is what you gain in time. Okay. And now I will change the mode a bit. The things which I couldn't talk at all in this set of lectures come tutorial, we always formed jets where all the nodes, so the graphs where all the nodes had equal kind of features. Each node had a position, some latent feature, etc. But in reality, when we look into detector distributions, there are some parts are ecal, some parts are hcal, and when you try to have the truth information, which part of the energies came from photons, which part of the energies came from pion, each of the nodes have different kind of features sitting on them. And this kind, if you want to encode this kind of variable feature distribution on the nodes, you can't live with a single graph, which is like homogeneous graph with similar features on it. You need to form structures, something called heterograph. Okay, I couldn't go into details because for many of you, graph neural networks were for the first time. But when you will do it now for your purpose, if such a situation appears where each individual nodes have different kind of features, that is a structure called heterograph. And you need to learn how to do message passing networks on heterographs. Okay, so this is, I'm just giving you examples. I don't have any more time to go into detail. Another structure, which is now my favorite, I'm interested in a problem called particle flow. And there, what we experience, when a truth particles enters inside detector, the signature it leaves are some detector hits and track hits. If you have seen an event display, you will see this. And what we try to do is to collect this information, club a subset of them, and form reconstructed objects. So when we have a notion in the real life experiment of a reconstructed hadrons, that hadron, that reconstruction algorithm takes inputs from some part of the detectors, some part from the tracker, etc. So there is an overlap of all this information, and there is a sharing of information between all these algorithms. So you can see this automatically makes it a set-to-set problem where different nodes of a set have overlap. And this structure, that's why we need to construct, is something called hypergraph. What is that hypergraph? Where you don't only connect two nodes by one edge, but probably you want to introduce a higher order structure where you collect few nodes and establish a relation between them all together to form not only a single edge was two nodes to one edge, but when you introduce abstract structures and notations like multiple nodes to one connection, that is called a hyperedge. And once a point cloud, a set structure has these hyperedges, those are called hypergraphs. And we are finding these structures are more and more appropriate for solving our complex problems. So when you will do it, you have to face it. And this is one of my favorite plot from my paper where we compared like different method of set attention versus hypergraph versus object condensation for particle flow. You don't need to go into all this, but I want to emphasize that in a set-to-set problem, you have to decide what is the structure which is most appropriate, whether it's a regular graph, whether it's a heterograph, hypergraph, and you accordingly need to do message passing networks on that. And also, if so when we talk about generative models, which we were talking, what we were trying to do. We had a collision event. I lost that stuff. We had a collision event which produced truth particles, and it passes through detector simulation, and we make our statistical analysis out of these reconstructed particles, right? So the whole conceptual level, the generative model is trying is to bypass this one and produce a fast simulation. And this were, so, and you remember that each kind of particle should give you a different pattern inside a detector. The nature of energy deposits of a single photon versus single pion is different. So when you write a generative model, you need to condition on the kind of particle which we started from. So often we face a problem of writing a constrained generative model. You can't write any generative model, but this kind of shower pattern should be constrained of the starting truth particle. So I'm just giving you some examples, and this is another example of what we wrote as a constrained generative model for truth particle, and we got some realistic distribution. If you are interested, you can look into this, and again I show you that what kind of loss functions you need to do. Okay, so this is end of particle physics stuff, and now I want to draw. I will take 5 more minutes to probably conclude. It's not only us, but other branches of natural sciences are using graph networks extensively. In fact, we are not doing anything compared to what chemists and molecular biologists are doing. Look at them. This is an example from cosmology. So here are the camel simulation for large-scale structures of the galaxy distribution in the universe, and they tried to infer the power spectrum for each galaxy using graph neural network. So here, whatever their analogous of Giant simulation called camel simulation gives them, the solid lines, and the dashed lines are what the graph neural networks give them. And if you search this paper, they also have their PyTorch geometric library, and you will see what you learned. They're exactly doing something similar. So once you know the general techniques of machine learning, you can do a lot of things, take just data from other fields which are also open, and try your skills in other kind of data sets without putting any effort. This is fantastic. Like 10, 15 years back, this was not there in the community, but now you can try. I'm not a cosmologist, so don't ask me. But they build, like the CMB spectrum, they build the power spectrum taking some Fourier distribution. So they just scan. I think they scan a particular Z epoch and some theta phi region in the sky, try to pick up whatever this large scale survey data gives them, and try to build a same power spectrum for all the galaxies they see. This is roughly what I understood, but I can be completely wrong. I mean, I just browsed their paper once, and this is what it was written. However, this is nice, right? Now, I want to highlight that there are a hell lot of graph data set present in this open graph benchmark, where they define different tasks of node level task, edge level task, graph level task, small, medium, large graphs, different branches of information. All these data sets are available. Not only that, they also provide you a custom data loader for each possible data sets. So you can try your own skills of building the neural network of your own. They will provide you the data loader, and you can play with them. If you want, life is open. Go through the details websites of PyTorch Geometric. There are all sorts of YouTube videos and Colab notebooks which will do far better job than I could do. So try them out. Also join their Slack. hundreds of people are interacting every day from all part of the world, all part of domain where they're using GNNs and exchanging ideas and informations and helping each other out. Why you shouldn't be part of that community, be it. Another one of favorite my library is DGL, so which has similar structure. Now, whatever work I have done and I have written papers, I have done all on DGL. So I picked up PyTorch so that this was my opportunity to learn this software in and out. So I just exploited you, okay? But I ensured that before coming here, I learned this also equally well so that I can answer your questions and give custom-made codes to you. So you can, DGL has the advantage that as a backend, you can use TensorFlow, PyTorch, or MXNet, whatever you like. But it's somehow less popular than PyTorch. I don't know why. Both are almost equivalent. There is another software called Giraffe, which is using JAX as backend. It's picking up, but it's still not as popular as one of these. Okay. And finally, there are fantastic community. Like I try to follow, they have monthly like reading sessions and discussion sessions. All their videos are available in YouTube, and whatever latest papers are coming out from top-notch people in this community, they are monthly discussed, and you can join the Slack as well, watch their videos. And I try to learn a lot from this course, and these people are like modern day genius of these fields. Try to follow their websites and whatever they put. You will gain, surely, if you have interest in geometry as well as the kind of machine learning we talked about, general set-based structures. These are pure gold resources. Try to follow them, okay? So that's all from my side. I hope I could give you a little bit epsilon of whatever I could. So hopefully you found this a bit useful. Thank you. Any questions from today? The last part was all storytelling, and the real GAN expert is sitting there. No questions? Okay, I'm here until Monday afternoon, so if you have further questions, you can catch me.
So I had a curiosity question. The map in GAN in general can be Rn to Rn.
Yeah, Rn to Rm, anything.
Yeah, Rn to Rm. For instance, for a particle generator, if we want to do in the space of 4 vectors, it's R4 to R4, let's say.
For single particle, but
for a single particle. Now, how does the time, all of this, as you go to higher dimensional spaces, it has a time and computing resource cost, right?
Sure. I mean,
so how does it go with the dimension?
It depends, like how you structure your model as well. Like when you write R4, it's your final output data shape, right? Output data tensor. But it also depends how many layers you stacked in between and how deep your neural network is. The feed forward time for processing one feed forward operation will scale up with that. So it depends on what you're trying to do, and there's no general formula I can provide you.
Yes, there is no curse of dimensionality.
The curse of dimensionality is there with even like a simple fully connected MLP kind of thing, right? So if you think of this, like if you are giving 4 dimension as input at an MLP and asking for 400 dimension as output, then the weight matrix is 4 by 400, and there are lots of sparsity going in, and you need to control the weight. So that's that's where the curse of dimension plays its role, and it's not necessarily controlled by the shape of the output data.
Okay. So we again had a great set of lectures from someone who is active and is an expert in the field. I hope you have all gained, and I could see that it has generated quite a bit of interest